The millwright operates the disconnect, believing the power is off.
Okay, locked out. Now to service it.
But the switch is broken inside. Without testing, he reaches in. A fatal mistake. He was authorized to lock, but not qualified to verify.
In the world of safety, procedures are everything. They're written to prevent the absolute worst from happening. But what happens when a procedure that looks perfect, one that you follow to the letter, is actually broken from the inside? That's what we're going to examine today. This is a tragic, real-life case study from the official records of OSHA involving an overhead crane.
And let's be perfectly clear. The events we're about to walk through are not hypothetical. They really happened. Every detail we'll cover is pulled directly from the official investigation. It's a sobering reminder of how a single hidden mechanical failure, when combined with one small human oversight, can completely bypass every safeguard we put in place.
So, our story begins on what should have been a completely normal day. The job was as routine as it gets, standard servicing and maintenance. You know, the kind of task that's done thousands of times in facilities everywhere without a single issue.
At the heart of this incident is a millwright, a skilled tradesperson. He's been assigned to do some maintenance work on a massive industrial overhead crane. For him, this wasn't some new or complicated assignment. It was just another part of his job, something he was fully trained and qualified to do. So, to get started, the millwright does exactly what he's supposed to. He kicks off the energy control protocol. We all know it as lockout/tagout. And this is the single most important safety step you can take. Its entire purpose is to isolate that machine from its power source, making absolutely sure it can't be started up by accident. He takes two very specific, very deliberate actions. First, he goes right to the main electrical disconnect and moves the lever to the off position. Click. Second, just like the procedure says, he applies his own personal lock to that device. That lock is a physical guarantee. It's his way of saying, this machine is under my control. Do not touch.
And right here, we get the first hint of the tragedy to come. And it's all hidden in that one little word, appeared. To the millwright, and frankly to anyone walking by, the job was being done by the book. The switch was off. The lock was on. The whole situation appeared secure. On the surface, it looked like every single safety box had been checked.
But underneath that appearance of safety, a hidden failure was just waiting, an unseen, and at that moment, an undetectable mechanical defect that was about to make all of those correct procedures totally useless.
The root of the problem wasn't some complex failure. It was simple decay. The internal parts of the disconnect switch lever were corroded, just slowly and silently. Over who knows how long, moisture and time had weakened a critical component, getting it ready to fail at the worst possible moment. And this is the critical result of that corrosion. On the outside, everything looked okay. The millwright turned that external lever and locked it right in the off position. But inside the box, the corroded part had completely failed, causing the external handle to physically break away from the internal switch. So while the handle he could see and touch was locked off, the actual internal part that controls the electricity, it never moved. It stayed stuck in the on position.
The outcome is just chillingly simple. The circuit was never actually broken. Despite the lock, despite the handle being in the right position, high-voltage electricity was still flowing to that crane. It was an electrically live and incredibly deadly worksite.
Now, to understand what happens next, we have to quickly talk about what an electrical bus bar is. Basically, it's just a solid metal conductor, usually a strip of metal, that's used to distribute a lot of electrical current. And on this particular crane, these bus bars, which were very much live, were located right near the bridge railings, the exact area where the millwright needed to work. So that corroded switch created the potential for disaster. But what turned that potential into a certainty was a second failure, this time a human one. It all came down to a critical omission, the failure to verify. Because he had performed all the physical steps, he believed the machine was safely locked out. He trusted what his eyes were telling him from the outside of that electrical box. And because of that, he didn't take that final step to actually verify that the power was off. And look, verification isn't an optional step. It's a non-negotiable rule of lockout-tagout. It's also a really simple process. First, you try to start the equipment. You push the on button to prove that it won't start. Then, for absolute certainty, you use a meter to test the circuit and confirm you have a zero energy state. We're talking about two simple actions that take just a few seconds. So the question is, was this final absolutely crucial step performed? The mechanical failure and the missed procedural step are now on a collision course. They're about to converge, leading us to the final, tragic moments of this event. A conclusion that was, when you look at it, entirely preventable. Let's just walk through that lethal chain of events one more time. It starts with the correct action. He initiates what he thinks is a safe procedure, but that is immediately undone by a hidden failure, the corroded switch. That dangerous situation is then locked in by a critical omission, the lack of verification, all of which leads to the final, unavoidable result. The millwright, believing he's perfectly safe, approaches a live, high-voltage conductor.
When he contacts the energized electrical bus bar located near the bridge railings, a fatal injury results.
All right, we've seen the tragic outcome. Now we have to answer the question that's on everyone's mind. How can a piece of equipment that's been locked out still be live? The thing is, the answer isn't just one single failure. It's a chain of them. So let's get into the investigation. So this is the real puzzle here, isn't it? The millwright did what he was trained to do. He went over and applied his personal lock. So why was that crane still hot? This wasn't a failure of his intent. This was a complete failure of the system, and it all started with a mechanical trap that was just hiding in plain sight.
The very first layer of this whole mess is the equipment itself. It was basically telling a lie, a mechanical lie, that created this fatal illusion of safety.
Okay, let's really break this down, because what you're seeing here is the mechanical heart of this entire incident. From the outside, the operator's view, everything looked perfect. The disconnect lever was in the off position, and the millwright locked it right there. But the actual state of things, inside that box, was dangerously different. That lever, it was so corroded that it had physically broken away from the internal switch stub. And that stub, which you absolutely cannot see from the outside, was still stuck in the on position. The bus bars were still fully energized.
So here's the bottom line. The integrity of your safety device is the absolute foundation of your entire safety procedure. If the switch itself is broken, that lock, it might as well be a piece of tape. It's just decoration. It gives you this false sense of security, which, honestly, is way more dangerous than no security at all.
So, let's move on from the broken hardware to the broken procedure. Because that mechanical failure, it created the hazard, but it was a procedural failure that actually led to the contact. And this is what we call the verification gap.
And this slide, this just lays out the gap between assumption and verification perfectly. The method that failed was based on assumption, just looking at the handle, a simple visual check. But the required method is all about verification. It's a technical check, using the right equipment, like a voltmeter, to prove that the circuit is de-energized. You don't trust your eyes, you trust your meter. Period.
Listen to this. This one sentence from the official OSHA case file, it just says everything. The employee does not attempt to verify de-energization. This wasn't a simple misstep. This was leaving out the one critical, life-saving action that could have changed everything. The procedure required verification, and it was just skipped.
So, why? Why was it skipped? Well, this question takes us to the deepest root cause, which is a systemic failure in understanding roles and responsibilities. This is the critical difference between being authorized to do a job and being qualified to do it safely. See, the millwright was considered an authorized employee. That means he was trained and given permission to apply that lock to that specific crane. He knew the lockout-tagout procedure for that piece of equipment.
But, and this is a huge but, he was not a qualified person. Now, this is a much higher level of competency. A qualified person has very specific training to work with live electrical parts and, most importantly, knows exactly how to test for the absence of voltage. This distinction, it's not just a bunch of jargon, it is a fundamental pillar of electrical safety.
And look, this isn't just a good idea or a best practice, it's the law. This entire situation was governed by OSHA's Electrical Safety Standard, 29 CFR 1910-33. This is the official rule book for this exact type of work.
And what's really interesting here is how incredibly specific the regulation is. It doesn't just say, hey, you should verify it. No, it says exactly who must do the verification, a qualified person. It says how they have to verify, by operating controls and using test equipment. The law explicitly required a level of competency that the millwright, as an authorized employee, just didn't have.
So when we put all these pieces together, the mechanical failure, the procedural gap, the competency gap, they all point to one simple, powerful, and absolutely unbreakable lesson.
It really is that simple. Test. Before, touch. This is the golden rule of electrical safety. It doesn't matter what the handle says it's doing. It doesn't matter if you put the lock on yourself 5 seconds ago. You have to prove without a doubt the absence of energy before you ever begin work. Okay, so let's walk through the safe procedure the right way. Step 1, isolate. You apply the lock. Step 2, assign. You make sure a qualified person is there to do the verification. Step 3, verify. That person uses their test equipment to prove the circuit is dead. And only then, after all that, do you get to step 4, confirm it's safe and begin your work. This is the sequence that saves lives.
So as we wrap up this analysis, the question you have to take back to your own workplace is this. Is your safety procedure built on assumption, or is it built on certainty? Because in the world of high-energy systems, that difference is everything.
Stay safe with HSEEG.